Hi, it is section 3.2, the Perceptron algorithm. The Perceptron is a binary classifier for supervised learning. In 1957, the method was invented by Frank Rosenblatt, Cornell Aeronautical Laboratory. It has been refined for hardware implementation, and in modern society, it becomes a basic unit for two-layer neural networks. Let's define the perceptron formally. We assume there are two classes, label 1 for positive class, label -1 for negative class. For the algorithm, input is a feature vector in Rm, and through the training, we have to find the W weight vector, and during iteration of training, G, the net input, will be made with dot product between X and W, so that it becomes weighted sum. Now, activation function is defined in this way with a threshold. If the net input is larger than or equal to theta, then the value is 1, otherwise -1. This is a formal definition of the perceptron. Here, activation function can be reformulated. Theta can be moved to the other side, then it's minus theta, and we use W0 for minus theta. Then now, along with the W0, this whole thing is called again the net input Z. Then if the net input is larger than or equal to 0, then the activation is 1, and otherwise -1. This formulation is the same as this one. Here, W0 is called the bias. The equation equals 0 represents a hyperplane in Rm, while W0 decides the intercept. Okay, we can understand it clearly when we consider the case m equal 2. Okay, net input Z equal W0 plus W1 x1 plus W2 x2 equals 0. If we are making coordinate x's, that is x1 axis and that is x2 axis, W1 and W2 will decide the slope of the line. Anyway, this is a line in two-dimensional region. And W0 will decide the intercept, so that here the line can be made in this way. And this is Z equals 0, and that is Z is larger than 0, and that is Z is smaller than 0, right? Anyway, the equation is representing a hyperplane, so that with a hyperplane, the Rm is separated into two parts. Right? Okay, here we have the perceptron learning rule. The perceptron is quite simple algorithm, and through training, we have to find the W, so that for given training data set, and now is the correctly predict and for every point. So we start with here weight 0 or small random values, and for each data point xi, we make a net input and activate So we can get here predicted label, and by using that we can update the weight. This is mathematical formulation, and here the weight is updated by using delta W, so that delta W is correction vector. The correction vector is defined in this way. Eta is the learning rate chosen between 0 and 1. Usually eta is a small number, very small. And yi is the true class for xi, and y hat I is predicted by using the current W, and now we can make here predicted output, that is y hat, and the difference is measured, and it is used for scaling the xi, the data point. To understand this rule more clearly, we need a simple thought experiment, a mind simulation. Assume in the beginning, for the current W, the perceptron predicts the class label correctly. That means that in the true class label is 1, then y hat is also 1. If it is -1, then it's again -1. Then the difference will be 0, so that the weight remains unchanged, because delta W will be 0, so that it's not updated. Now we assume that the perceptron makes a wrong prediction for xi using the current W. That means that if it is 1, then it's -1, so the difference is 2. And if it is a -1, then it is 1, so that the difference is -2. So it changed into eta plus minus 2 eta xi. If we write the correction vector component-wisely, the jth component will be written in this way. Okay, let's try to understand that correction term. Okay, now for xi, ith data point, and assume that for every point that is now positive. So practically, in particular here, the jth component of ith data point is positive. And now we assume here ith label is 1, assume that. But the current W, along with the current W, and perceptron makes a wrong prediction. And that means here, okay, wrong prediction means that yi hat equal -1. And then here, from this one, now delta Wj will be now, okay, this is 1 and -1, so that it is 2. So that is 2 eta and xj and I, like that. Okay, so from this one, now Wj is same as Wj plus delta Wj, so that Wj is increasing. Then later in iteration, this increase means that now the net input, and because the W is increased, and once that is used, now the increased W, and along with the same here ith data point will be increased, because we assumed in the beginning positive, so that along with increased weight, the net input will increase, right? If it is negative, then you may think the same logic, but similarly you can simulate your mind. That is increased. That means that here its activation is earlier. The activation value is -1, but because now z is increased, so that there is some possibility that -1 change from -1 to 1, right? Because now w is increased, so that for the point, net input is increased, so that activation currently is -1 because it's negative, it's -1, but it's increased, then there is some possibility to be 1. Then it becomes 1, then is the correct prediction. So in this way, the W is updated to make a correct prediction. Okay. It is known that the perceptron converges only when the data is linearly separable and learning rate here lambda is sufficiently small. So what is linearly separable data set? Here we define linearly separable data set. A data set xi, yi, the feature vectors and label is linearly separable if there is a weight w hat, some special weight vector, and gamma, a constant, such that now this dot product with the label, of course over there label is 1 or -1, so that once it is in positive class, then this will be positive and yi will be 1, so that anyway positive. If xi is in negative class, that one will be negative, and because -1, again that will become positive. This value is larger than or equal to gamma, and gamma is positive for every point, and if there is such a wave vector and now constant, so that satisfying this inequality, then we say the data set is linearly separable. Pictorially, now this parameter gamma is playing the role of margin for this strip, so that there's half a margin is now gamma, and again gamma, and the data points are here, out here for one class, and for the other class, the other side. That picture is illustrating the linearly separable data set. And more formal, traditional definition can be given in this way. For two data set, and here, if there is two data set, then we can say that x, y are linearly separable if there are real numbers, and 1 to m, w1 to wm, and k, such that for points in x, one set is now that product is larger than k, and for the other set points, the dot product is smaller than k. So here, in m-dimensional space, now w dot x equal k is a hyperplane, and this is now separator of a data point, so that x will be one side y will be the other side, right? In this case, we say that the whole data set is separable, linearly separable. Okay, here we have a theorem for perceptron. Assume that the data set and xi, yi, future vectors and label is linearly separable with margin gamma. And that means that here, by using that definition, and the assumption is the same as this one, there is some special weight, double hat, and we can scale it so that its norm is 1. And now double hat and xi for every point, and the dot product and label multiplication is larger than or equal to here gamma, and that is assumption. And suppose that now the data values are bounded by R in L2 norm for some R, then maximum number of iteration, so that maximum number of mistakes and predicting wrong label made by Perceptron algorithm is bounded by R squared over here gamma squared. So that before such iteration, the perceptron will converge. Okay, let's see proof a little bit. Okay, now assume that perceptron algorithm makes yet a mistake for that L data point. Then that means that once it is updated along with that one, then updated weight vector will be W L plus 1. So that is the same as this one by this update rule. And now there's a norm squared of the vector is same as basically this whole thing and dot product with itself. So you can write in this way. Here the norm of this one squared, the norm squared of that one plus twice that dot product. So you can write in this way. Now here for that one, and here that is always, this one is always non-positive y, because we assume that is wrong, so that means that here if it is 1, 2 to 1 is 1, then now that is minus 1. The reason we are making minus 1 is that is negative, right? That net input is negative, so that we are making negative. So 1 minus 1, so that is 2 times negative. So that here, this cannot be positive. So in inequality, we can ignore that one. So we recheck that. And then here, now, okay, there's this squared. And again, for each one, okay, that is now, okay, this one can be easily written in this way. There's eta, that is plus minus 2, so it is maximum is 2, and we already know that this one is bounded by R, right? So that is squared, so we can reach that one. Okay, and that is W L plus 1 squared is bounded by the earlier W squared plus that, so that if you go one more time, to start with WL squared, and that is again bounded by Okay, this one will be bounded by WL minus 1 and norm squared plus 2 eta R squared. So we have one more, so that you can put over there 2, right? So that go to the 0 and go to the up to 0. Then if we start with the initialization with 0, then eventually L times later we stop here. And now existence of W hat is already assumed, so that rather than measuring L to norm squared, we try to measure dot product along with W hat. And then again, with some algebraic manipulation, you can reach at this inequality, so that again, by using the same logic, you can reach at that. Okay, so from these two, you can conclude the final upper bound. Okay, here we have a properties of the Perceptron algorithm, and yet the separability. Some weights get the training set perfectly correct. Once the data set is separable, then you can find the weight vector so that here for every point in training set is perfectly correct. And also convergence is now, if training is linearly separable, then now Perceptron will converge eventually in a certain moment, because we already know that the upper bound of iteration is given in this way, so that eventually it is convergent once the training data set is linearly separable. Okay? Okay, this is the first part of the section. We'll continue in the second part. Thank you.